Hi there, ladies and gentlemen. Just want to walk you through very briefly an important concept. It doesn't take long to discuss it, but it is really important. Do you understand the difference between when you should use the Pythagorean theorem and when you should utilize the special right triangle ratios? So that's really, really important. Want to just walk you through a couple examples that'll kind of show you the difference between the various scenarios that could pop up. Nothing really new in this video, but just kind of taking what we already know and applying it and making it very clear what those differences are. So if you look at number one, it says to use the diagram below, we want to find the length of the ladder leaning against the wall. Round your answer to the nearest tenth of a foot. So the first thing you want to do here is you want to notice the characteristics of the triangle you're looking at. I notice there's a right angle. I notice there's a 60-degree angle. Knowing that a triangle's angles have to add up to 180 degrees, I can guarantee you that this is a 30-degree angle. I know I am dealing with a 30, 60, 90-degree triangle. Okay? So that being the case, we can utilize those special right triangle ratios. Okay? This is my long leg. This is my short leg. So I want to take a moment to identify those. Right? I know that whatever this is times the square root of 3 gets me this. So I can write an equation that says that, right? The short leg, y, times the square root of 3 gets me the long leg, which in this scenario is 17 feet. Right? So if I divide both sides by the square root of 3, I have my long leg. Now I want to find the length of the ladder leaning against the wall. That's this length, or in my right triangle, that's the length of the hypotenuse. If I know my right triangle ratios, I know the hypotenuse is 2 times my short leg. I know what my short leg is, I just found it. So my hypotenuse, x, or the length of the ladder leaning against the wall, however you want to look at it, is equal to 2 times whatever y is, and we know y is this, 17 over root 3. Now we are allowed to round to the nearest tenth of a foot, so you'll notice I'm not going to simplify this, right? I'm not going to take the time. If it said to write your answer in simplest radical form, we'd have to do, all right, this is like 2 over 1, 2 times 17 is 34, 1 times root 3, and then I'd have to do the simplification process where I multiply by this funky looking form of 1, and I end up here, right? That would be if it asked me to give an exact answer or an answer in simplest radical form. But I don't need to do this, right? Kind of awesome when they tell you can round because you don't need to do the simplification process. Pop that into your calculator. Round to the nearest tenth of a foot, and you're done. Right? If you pop that into the calculator correctly, it should be x is equal to 19.6 feet. The other thing you might want to notice in this one is I can't use Pythagorean theorem to deal with this triangle. Right. The reason I can't, if I want to use the Pythagorean theorem, I need to know 2 of the 3 sides. Right? I have that relationship a squared plus b squared equals c squared. I need to know a and b if I want to find c. Right? Similarly, I need to know a and c if I want to find b. Right? You need 2 of the 3 variables in the Pythagorean theorem to find the third one. The special right triangles, those ratios are a little bit more powerful in that you only need 1 side length to find the other 2. So that's one of the big differences between Pythagorean theorem and the special right triangle ratios. All right, if you'll move down to number 2, we have another example here. This one asks you to find the perimeter of triangle ABC. It says to give your answer exactly and to the nearest hundredth. Take a moment, go ahead, try it yourself, see if you can figure it out. All right, hopefully you had a moment to go ahead and give it a shot. Please notice, again, you have to observe the triangle and its characteristics, right? The only thing I know about this triangle is it's a right triangle. I don't know if this is a 30, 60, 90. I don't know if it's a 45, 45, 90. It might be a 72, 18, 90. I don't know. All I can tell you for sure is that this is a right triangle, right? That's all I know. Since it's a right triangle, I can go ahead and use the Pythagorean theorem, right? I know that the length of the leg squared plus the length of the other leg squared is equal to the length of the hypotenuse squared, right? That's what I'm saying in symbols right here. Okay. All right, so I go ahead and plug that in. Well, I know one of the legs, 32 squared, plus, we're going to leave it b squared. I'm going to call this lowercase b, right, is equal to 45 squared. All right, you can use the calculator really quickly if you like to, and get these numbers squared. I'll do the same here. So this is 1,024 plus b squared equals 45 squared, 2,025. All right, I'm going to subtract 1,024 from both sides, and that should get me to 1,001. Square root both sides. B is going to be equal to the square root of 1001. So that's the length of this side, right? This is equal to square root of 1001. All right, we want the perimeter. We want an exact answer, and we want an answer to the nearest hundredth. Well, my exact answer, perimeter, would be 45 plus 32 plus the square root of 1001. I can only reduce these, right? This is 77 plus square root of 1001. Right, some units, I don't know what they are, I know they're one-dimensional. This would be my exact answer. Okay. Some people will try to combine all three of these. These are like apples, these are like oranges. Right? I can't add 5 apples to 10 oranges. It doesn't make any sense. Same thing here. Numbers outside the radical can be added together. Numbers in the radical can be added together, but I can't add numbers outside the radical with numbers inside the radical. They're different. Okay. So this would be your exact answer. If you wanted you to round your answers to the nearest hundredth, go ahead and pop the 77 plus the square root of 1001 into your calculator. To the nearest hundredth, it's approximately 108.64 units. Okay. So that would be to the nearest tenth. Now again, notice I can't use the special right triangle ratios in this one, right? Because I don't know what kind of triangle it is. I have nothing here that tells me. So all I can do is, hey, I know it's a right triangle. I know the Pythagorean theorem applies. Let's use it. Okay. And again, the nice thing here is I know 2 of the sides. So that also allows me to use the Pythagorean theorem. All right, last example we want to show you here. If you read this one, it says, find the area of an equilateral triangle with sides of length 16. Give your answer in simplest radical form and round it to the nearest tenth. So let's go ahead and sketch an equilateral triangle. All the sides are 16. Right? All the angles are 60 degrees. All right, so area for a triangle. Let's think this through. I need 1/2 the base times the height. Well, the base of this triangle, I can pick any side to be the base of the triangle. Whatever side I pick, it's going to be 16. I'll pick this one for ease. Now the height, remember the height is the length of the altitude in a triangle, and the altitude is the segment drawn from the vertex opposite the base, and it's dropped down to the line containing the base, so it's perpendicular to the base. I don't know the length of this altitude segment, right? But you know what? I can find it. Since this is an equilateral triangle, when I drop this altitude down, I know it splits this triangle into 2 congruent triangles, right? In particular, it splits this angle into 2 congruent angles. 30, 30. Right? By definition, I drop this down at a right angle, so I know this is a right angle. I know this is also a right angle. So really what I have here is 2 30, 60, 90 triangles that I've split this up into. Conveniently enough for me, I know my special right triangle ratios for 30, 60, 90. Only problem is, right now I just know one of these lengths, right? All right, well, since I split these up into 2 congruent triangles, I can look at this one of 2 ways. Since I split this up into 2 congruent right triangles, I know these have to be congruent. I know they have to add up to 16, so this must be 8 from here to here. And likewise, this must be 8 from here to here. This is the short leg in my 30, 60, 90 triangle. This is the long leg in my 30, 60, 90 triangle. Right. So I take whatever the short leg is in the 30, 60, 90 triangle, and I multiply by the square root of 3 to get the long leg. So I know the height of this triangle is 8 root 3. Now, alternatively, and this is a pretty cool scenario because I can actually use either here. I can use the special right triangle ratios, or I can use the Pythagorean theorem here. I think it's quicker to use the special right triangle ratios, right? And I'll show you what I mean in a second. But we did find the height, right? It asks for a simplest radical form answer and a nearest tenth answer. Half of 16 is 8. 8 times 8 is 64, and I leave the root 3. Right? So that many square units. That's my exact answer. Approximate answer, and we want this to the nearest tenth. Go ahead and pop that into the calculator. 64 times the square root of 3 should be about 110.9 square units. All right, so a couple things to touch on, right? I said I could have used the Pythagorean theorem here. Very possible, right? Once I figure out this is 8, I can use and I said there were 2 ways to figure out this was 8. The way I mentioned was I knew this was 16. I knew these are congruent triangles. Split it 16 in half, right? I get 8. The other thing you could do is you could say, hey, this is a 30, 60, 90. I know that for sure. This is the hypotenuse of that 30, 60, 90. I know that the short leg in a 30, 60, 90 triangle is half whatever the hypotenuse is. So 16 divided by 2, 8. So you could have done that way. Now, once I know this is 16 and this is 8, I can still figure this out. But look how much longer this is, right? So yeah, I can use the Pythagorean theorem here, but is it really the most efficient thing for me to do in this scenario? So this would be a leg. My height, right, I'm going to call B. I wouldn't know that. And I would have known that the hypotenuse was 16, right? So this is 64 plus B squared gets me 256. Right? And B squared is going to be equal to 192. If I square root both sides, well, now I got to simplify this thing, right? Oh man, here we go. All right, so 192. Let's see, that breaks down into 8 and 24. And so I get an 8 and 8 and a 3. Alright, so I think I got it, right? Square root of 192. Square root of 8 times square root of 24. Square root of 8 times square root of 8 times square root of 3. Square root of 8 times square root of 8 is 8. So that would have been my height. If I do all this work, take the time to reduce, I get B is equal to 8 root 3. Whew! Man, I'd rather use that special right triangle ratio back up here and just say, you know what, I got the short leg, it's 8. If I multiply the short leg by square root of 3 in a 30, 60, 90 triangle, I get that long leg. That's a heck of a lot easier than doing all this to figure out it's 8 root 3. So this is an example where I can use either, but as you will see, those special right triangle ratios, man, are they efficient sometimes. You can really save yourself a lot of work by knowing that concept and knowing it well.